This cross-section shows a standard, naturally aspirated engine. As the piston moves downwards, it creates a vacuum, relying entirely on everyday atmospheric pressure to push outside air into the cylinder. Because it is bound by the weight of the Earth's atmosphere, the engine can only inhale a fixed amount of oxygen with each stroke. Internal combustion relies on a specific physical equation. To burn more fuel and generate higher power, an engine must ingest more oxygen. By packing more air into that same cylinder space, the engine ignites more fuel, causing the torque output to spike upward. Engineers realized that relying on ambient air pressure was a physical bottleneck. To break past the limits of the atmosphere, they needed a mechanical method to forcibly cram oxygen into the intake. They called this forced induction, and the supercharger was the first practical application of that concept. Since an internal combustion engine is essentially an air pump, its power output is physically restricted by its oxygen supply. Using mechanical force to overcome that natural ceiling turned forced induction into the primary solution for high-performance engineering. The technology to force massive volumes of air didn't start in automobiles. In 1860, brothers Philander and Francis Roots patented a heavy-duty industrial air pump designed strictly for ventilating mine shafts and powering blast furnaces. It took 25 years for that industrial concept to reach the internal combustion engine. In 1885, Gottlieb Daimler patented a gear-driven air pump specifically for engines, creating the first practical supercharger design. By World War II, forced induction became a necessity for aviation. Aircraft flying at high altitudes encountered air so thin that standard engines lost most of their power. Superchargers compressed that thin atmosphere, allowing fighter planes to maintain engine performance miles above the ground. During the 1920s and 30s, this technology migrated to road racing. Manufacturers like Mercedes-Benz bolted superchargers to cars like the SSK, establishing a higher performance standard for endurance racing that would influence automotive design for decades. From blast furnaces to high-altitude combat and dirt tracks, mechanically forcing air into a combustion chamber proved to be a reliable method for increasing engine output across diverse environments. This layout shows a supercharger. An air compressor on the intake is connected directly to the engine's crankshaft by a heavy belt. Because they're physically linked, pressing the throttle instantly spins the compressor faster, shoving pressurized air into the cylinders. This creates a unique power curve. Unlike standard engines that must wait for RPMs to climb to cool in more air, the supercharger forces that air in immediately, generating a predictable surge of torque at low speeds. This direct physical tether between the crankshaft and the compressor is the reason a supercharger achieves immediate throttle response. This is a classic Roots-type supercharger sitting on a modern V8. It is a staple of American muscle cars because its internal rotors produce massive amounts of boost at low engine speeds. The twin-screw supercharger is a more efficient variation. It looks similar from the outside, but its rotors actually compress the air as it moves through the housing, which lowers the temperature of the air entering the engine. Finally, the centrifugal supercharger uses a high-speed impeller. Its boost rises linearly as the engine spins faster, making it most efficient at high engine speeds rather than off the line. For heavy-duty applications, the instant low-end torque of Roots and twin-screw designs is an ideal engineering solution. Moving a heavy trailer requires immediate rotational force to get the load started, which a belt-driven compressor provides reliably. Trucks like the Toyota Tacoma X-Runner and the Ford F-150 SVT Lightning utilize these unique torque curves for specialized hauling and performance capabilities straight from the factory. These three distinct compressor geometries show the mechanical versatility of the supercharger, allowing engineers to match the air delivery to the specific needs of the vehicle. This mechanical connection has a significant cost. Driving the compressor off the crankshaft requires physical work, consuming engine horsepower, a loss known as parasitic drain. Additionally, compressing air generates extreme heat, raising cylinder temperatures, which increases wear and can lead to engine failure. To manage this extreme thermal stress, many systems require intercoolers. These work exactly like radiators to lower the temperature of the intake air, adding significant complexity and weight to the engine bay. Because the system must consume its own power to generate more, supercharged engines have an inherent ceiling on their maximum efficiency. To solve the problem of parasitic drain, engineers increasingly turn to the turbocharger. In this diagram, you can see how a turbocharger functions. Instead of drawing mechanical power from the crankshaft, it captures thermal energy from exiting exhaust gases to spin its compressor. It effectively recycles waste energy to force air into the engine. However, the turbocharger has its own drawback. Because it relies on exhaust gas, there is a delay, or lag, between when you press the throttle and when the turbine spins fast enough to provide boost. The two systems represent different priorities. The supercharger trades efficiency for immediate throttle response, while the turbocharger sacrifices instant hit to achieve better fuel economy. Modern automotive engineering is governed by strict fuel economy and emissions laws. Manufacturers now prioritize extracting the maximum amount of power from every drop of fuel. As a result, the industry has almost universally moved to turbochargers. They offer higher thermal efficiency than superchargers because they do not constantly drag on the crankshaft's power. This shift has made factory supercharged vehicles relatively rare. Over the last 20 years, they have been largely phased out of standard production, remaining mostly in high-end luxury cars or extreme muscle cars like the Camaro ZL1. The technology followed a path from industrial mineshafts to high-altitude combat and eventually into the world's fastest road cars. While modern emission standards have made it a niche choice for daily driving, the supercharger remains the most direct mechanical solution for drivers who prioritize immediate belt-driven power.